Hello. Thank you, Professor Kondo, for the introduction. And thank you, everyone being here for the last talk before the launch. I'm Xulong from University of Pittsburgh. I'm present for my student, Yingheng, and due to visa and internship, he cannot come. And by the way, he's doing compiler quantum compilation work, and he'll be on the market next year market. So if any opportunity, please kindly reach out. All right, so back to the talk. So I'm going to talk about the work of reinforced learning guided graph state generation in photonic quantum computers. So starting from the basics, so we all know that now superconducting is still dominating, but there is a rise for other type of quantum computers like ion traps, neutral atom, and photonic, and so forth. Compared to them, there are some advantages of photonic quantum computers, like a faster execution speed, long coherence time, and easy integration with the quantum network, and part of the photonic quantum computer can operate in normal temperature or room temperature there. And not just stating academic, the photonic quantum computer is also real. For example, 3 examples here. One from China, USTC, they have the version 3 Zhang quantum computer with 255 photons here, and also the PsiQuantum computer and Xanadu. I remember that 2 years ago, there is access to the Xanadu photonic quantum computer from the Amazon bracket, but 1 year happened ago roughly, they offline the machine to calibration. I have no clue when that will be back online, but that's something real in the world now. So to realize the quantum circuit in the photonic quantum computer, so one basic thing is to construct the physical constructor called graph state. So in a graph state, each node or circle here represents basically 1 photon, and the edges between the photons represent the entanglement between the photons using the CD gate. And after generating the graph state, so the next step is basically to apply the merriment on top of the photons, which will destroy all the photons. And the information will carry from photon to photon like a ripple propagation from the input photon to the output photon there. And therefore, like I said, so to realize the quantum computer there are 2 steps here. One is generate a graph state. The other one is apply the merriment. I mean, both steps are not perfect. There are errors associated and performance issues here. So for this paper, our focus is the generation phase of the graph state there. So before going into the detail, let me give you a high-level summary or cap here. So the graph state generation is very important to the performance and fidelity. And but there is multiple ways to generate the graph state. The generation sequence is not unique, and it has a large space, which I will elaborate later. And in this project, basically, we propose a combination of reinforced learning and graph neural network to guide this generation sequence, which reduce the search space and also generate a graph state, co-optimize different metrics here, which also we'll expand later. And results compared to the baseline, which use the stable level metrics to generate kind of like an exhaustive search, and it performs much better in the optimization results in terms of error rate and also in terms of performance. All right, so I'll spend some time on background because I think this is important. And the approach part, I will be a little bit simplified due to the time. So to generate the graph state, there are 2 main ways here. One is using fusion operations. The other one is using quantum meter, which is a physical device here. Well, there are a bunch of work doing the fusion operation. The fusion itself is not perfect. It's the errors here, and if you fail there, you have to regenerate graphs there. So in this paper, we focus using the physical emitter, quantum emitter, to generate the graph state. So in this figure, the square is the emitter, and it can pop out entangled photons, which annotated as a green node here, and to generate the graph, a target graph we want. So according to physics MPI Quantum Information Journal, there are 6 operations that we can use to generate the graph. For these 6 operations, you can treat them as the 6 pieces of the, like in the Lego game, the 6 basic pieces we can apply or use to generate a target complicated graph here. So let me explain each of them quickly and in a little bit more detail. The first one is called emit and mirror, which means that the emitter itself can pop up the photon, the green node here, and then mirror the emitter itself to eliminate the emitter from the graph. This usually is in the last step when we're going to finalize the graph state there. And second one is called type 1 emission. It means if the emitter can pop up the photon and entangle with the pop-up photon there. And third one, type 2 emission. So the emitter can pop out the photon in a kind of star fashion, not like a linear fashion in the type 1 emission there. And type 3 is looks like a little bit magic there. So the emitter can actually pop out the photon, and that photon will entangle with all the other neighbor photons of that emitter here. And the fifth one is a CD gate, which applies entanglement between two emitters here. And the last one is called type 3 CD gate. If we have 3 emitters here, it can apply 2 H gate on A and 1 H gate on B, and apply CD gate between A and B, and this will create entanglement between the emitter B and C in this case. Okay? So this is the kind of normal order using emitter to generate the graphs, and these 6 are the basic operations here. And I copied exactly the same 6 operations here in these slides, and according to a recent study, they actually want to use a reverse order to explore the generation sequence. The benefit I will explain in the next slides. So correspondingly, I just first illustrate the reverse order there. So instead of like emit and mirror, where you remove the emitter there, it's like a snake game now. You have an emitter here, and you can eat a photon there. Well, this is not a generation sequence, just to explore how the graph can be constructed. And same for type 1 emission. So in the base one, you pop out one and entangle with a photon, and in this case, it's like a snake. You can eat that photon here. And also, you note that there are text there, basically adding some constraints to each of this reverse operation that will simplify the search in next slide I will explain. Same for type 2. It's pop out the photon in the normal order, and here you basically eat that photon, kind of absorb it. And same for the type 3 reverse CD gate and type 3 reverse CD gates. Okay? So again, this is nothing different from the top one, it's just that the order is different. So why we have this reverse order, why this is important? So if we look at the normal order, if this is a target graph, very simple as a triangle here, what we have to do is that we start with one emitter, and if we try to use type 2 emission, it will pop out one photon there, and pop another photon here, and now we're stuck. There's no way for us to entangle these 2 photons there, because from that 6 basic operations, there is no opportunity for that. So this is failed, and we have to do another try. So in this attempt, let's do type 1 emission here. It's like linearly pop out the photons. And again, when we end up with this kind of shape, there is no way to entangle that emitter with the photon. So we have to retry again. So using this kind of normal operation order, we end up with a lot of retries. So according to the recent study, it's important to use a reverse order such that we add the emitter to that photon there as the first step. We have to put the emitter in the graph to eat that photon, right? And now, because of the constraints, all the text there are basically saying that the type 1 and type 2 observation cannot apply to this graph because of they does not satisfy the constraint. And what we have to do is that have another emitter here to eat that photon. And then we can apply like the reverse CD to remove that edge, and then use a type 1 observation to eat that photon, and another reverse CD to remove these two. So this is just a reverse order to look at how the graph can be generated. In generation, it's still in the in-order sequence once we have the order identified. All right, so basically, according to that 6 operations, this is the kind of the gates you apply to the emitter or the photons to realize that operation there. And put it all together as a simple example. So if this is a target graph, we have an emitter swap here that will add a bunch of gates here to the emitter and the photon there. And then you have type 1 absorption, and which will add another part there, and so forth. So at the end, that is the generation sequence of the target graph state. And by the way, the 2 Hadamard gates here can be canceled. So this will be removed. This is the generation sequence. All right, so with this in hand, with this kind of background in hand, so I want to talk about the motivation of the work. So there are three things we care most during this generation sequence. One is the generation time. The other one is the number of the emitters we use, the physical emitters we use to generate the graph state. And the third one is the number of CD gates. Remember, the CD gates is used to entangle the emitters or the photon with the emitter. And why they're important, why we care them most, because they correspond to the fidelity of the error here. So according to the equation here, the fidelity for decoherence is listed in that equation there. So at high level, there are two things important here. One is the circuit generation time. The other one is the number of emitters. So the shorter generation time, the better, the lower error rate, better fidelity. And the fewer number of emitter counts here also is good because the emitter can also cause errors here. And T2, by the way, is a constant determined by the physical emitter itself. Second, the fidelity of the CD gates. Remember, the CD gates is used for entanglement between the emitters. So again, at high level, fewer number of CD gates will be beneficial compared to using more CD gates. So with this in hand, if we look at the same example, there can be multiple ways we generate this graph. So I'll show one here. It's basically using this order to apply all this information here. And this is end up with generation time, the number of emitters to use, and number of CD gates here, okay? And why this is long here? Because physically applying the CD gate takes much more time compared to other operations here. In the bottom, we use another generation order. And first, of course, every time first we need to swap an emitter into the picture. And instead of having two emitters, we can have one there and then apply type 1 absorption here. And this will end up with the generation sequence showing in the bottom. Why this is good? If you count in this case, the generation time is shorter because there's no CD gates applied between the two emitters. The number of emitters used there is also less compared to the top one, and there is no CD gates applied there because you only use one emitter. Well, this is a toy example. I mean, using exhaustive search is easy to identify the bottom one, but giving a complicated graph, this search space can be super large. That's something we're targeting to reduce and solve. So if this is the case, the goal here, high-level goal, is to find a generation sequence that collaboratively reduce the three metrics we care here. Again, the generation time, the number of emitters used, the number of CD gates involved. So the challenge here, as I already mentioned, is a large search space because we have 6 operations in each step. Even for this toy example, it can branch out. And if it's a complicated graph, there are so many options there. And actually in the baseline stabilizer solver metrics, they use kind of exhaustive search. So we will show the comparison later. And the question becomes how to identify the good generation sequence efficiently. So naturally, we combine the reinforced learning and the graph neural network to do that. Why graph neural network? I mean, graph state is graph structure and is well aligned with graph neural network to encoding the information there. And why reinforced learning? Because we find that using just a small circuit, small size circuit, can actually well train a 3-level MLP in the Q network to help identify in large circuits, which we will show in the evaluation. I'm not intending to give a tutorial for the GNN or the reinforced learning, but I want to emphasize this is a basic flow for reinforced learning, and we use that Q value, which is a reward function, to guide the generation sequence. And for training, as I mentioned, we use a small size circuit to train the Q network, and we apply inference on any unseen applications and unseen number of qubit count there. And this is a summary of why this is good here. I just want to show the reward function we use in the reinforced learning. So it looks complicated, but if we break down, it becomes a little bit simple there. So the purpose here is that the state is basically the current graph at which state we're generating. And the action is basically among the 6 reverse operations we apply there. And the next state is S prime here. And the R value there is basically a combination of the 3 targets we use there. And we did a sweep later to show for different alpha what is emphasized on optimizing different target there. And to briefly mention the training phase, so first we do offline training, use small size circuit. We don't do online training there. And in the experiment setup, let me pop out the animation here. In the experiment setup, we use 300 episodes here. And at the beginning, I mean, each of the episode consists of 2 steps. One is the experience phase, one is the model training phase. It's typical in the reinforced learning. And in the experience phase, we choose the epsilon starts with 1. So every time we choose a random operation and learn the reward to put the reward in a kind of database. And then gradually we tune down this epsilon, and towards the later episode there, so it will start using the Q network to predict the operation there. And for inference, starts with a target graph, and we use the Q value to guide which action to take in each state. And that will lead us to the optimized generation sequence there. So due to the time, I don't want to expand too much on the reinforced learning, but you have more details in the paper. For example, the formalization of the problem into a reinforced learning problem. And also, if the graph is super large, even apply reinforced learning and GNN, the time is not scalable. So we leverage some concept called reception field to locally optimize part of the graph while leave the others to next step. And there's also a very detailed running example to help understand the entire flow in the paper. So if you're interested, I encourage you to read the paper there. So come to evaluation. So here I want to mention is that, interestingly, we only need to use this, we call each 6 benchmarks here, and each of them we have small, medium, and large in terms of qubit count. We only need to use 3 small sized benchmarks to train that Q network, and all the rest we can use for inference. And surprisingly, the results is pretty good. The reason behind is basically the graph have some shared similar data structures, no matter how large the graph is. And here is in terms of the 3 metrics optimization, and compared to the baseline, uniformly we're reducing. And one interesting finding is that compared to baseline for the number of emitters, the reduction is comparatively small compared to other 2. This is because for stable level solver, they only optimize for the minimizing of the number of emitters there. So that's why that's our top optimization target. So compared to them, the achievement is smaller. And scalability. So showing here, this is the benchmark set we use for scalability in terms of logic qubit count and the graph state number of nodes and edges here. And the top figure there shows when we scale the number of photons there, how long time needs to find the generation sequence. And we use 24 hours as a deadline there. As you can see that for stable level solver, most of them beyond 1,000 cannot be finished in 24 hours. But using this reinforced learning and GNN, we're able to achieve 7,000 photon graph within 24-hour limit. And bottom shows that even with the increasing of the photon count, the reduction for the 3 metrics is basically also remarkable there. And because we're collaboratively optimizing 3 target there, 3, the generation time, emitter, and the number of city gate there. So we use a Pareto model to show that how good the results is. So towards the 0, 0, that's optimal one. And the greedy one is shown the green here. And you can see that the reinforced learning approach, which is orange node here, which is close to the optimal. So for other results, please find in the paper like complexity, discussion, sensitivity, and so forth. Come to the conclusion. So the graph state generation sequence is important, and search space is large. The baseline is exhaustive search, which have performance issue and also fidelity issue. So in this project, we use a combination of reinforcement learning and the graph neural network to guide the generation order. And the results shows that it is close to the optimal and outperforms both baseline and gradient approach. So I think that's all for today. I mean, I'm happy to take any question. Thank you.
Thank you.